Hey, Lorenz, can you hear us?
Can you hear me now?
Yep. Could you please give us like maybe a couple of minutes? We are trying to figure out
Sure.
that.
No.
Thanks.
I'm gonna try to share my screen to
Yeah.
see if it.
Yeah. Somehow we still can't see you, so something on our side.
Oh, okay. I think my video's on, but
Yeah, I think it's a problem on our side. We're still trying to set it up.
the screen sharing seems to work. Do you see my screen?
I think we see it in the laptop, but we're trying to project it as well. So
Nice.
yes, now we can see you.
Right.
Yeah. Could you try sharing it now, maybe?
Yeah.
Yeah. Perfect. Okay, well, welcome everyone to today's string seminar, and sorry for the delay, Lorenz. Yeah, we're very happy to have Lorenz Eberhard with us today. He's going to tell us about a localizing AdS3 sigma model.
Okay. Thank you very much. Thanks very much for the invitation to, unfortunately, I'm only there virtually, but hopefully we can make it as interactive as possible. So please, I understand, I think some of your...
Lorenz, sorry, could you just drag your video window on your iPad, maybe, if that's possible?
Sorry, you want me to turn on the videos on the iPad?
No, yeah, on the iPad, maybe you can just push it to the side.
Okay.
Yeah, perfect. That's all. Yeah, thank you.
Right, yeah. Okay, yeah, so please feel very free to speak up, write in the chat, or um, get my attention any other way. Okay, so today I'm going to talk about a paper that I put out with Matthias Gabadil recently, but I will also mention some earlier work that I think is necessary to understand what's going on. Good. So let's start in the beginning. And we have probably all heard about the AdS-CFT correspondence. And one particular instance of this correspondence is the case of AdS3. And so there are several string backgrounds involving AdS3. The one that I want to focus on today is AdS3 times S3 times T4. And already in the original paper of Maldacena, he explains that the dual CFT to this string background is the symmetric obifold of T4. But I want to emphasize, I wrote this funny arrow here because both sides of this correspondence have a lot of parameters. So in fact, there's a 20-dimensional moduli space on both sides. Some of those moduli are easy to understand. They're just describing the shape of T4. Some of the moduli are more complicated. But the arguments in Maldasena's paper just tell you that the string theory is on the same moduli space as the symmetric obifold. So this is a very special point in moduli space. And similarly, on this side, we can turn on many of these moduli. And I think it's fair to say that only parts of this dictionary are known. So in particular, it's not completely known how these 20 parameters on this side are mapped to the 20 parameters on this side. Because of this, you can often only check things supersymmetrically protected quantities that don't depend on these moduli. So there are many, many papers in the literature where, for example, the BPS spectrum is checked, various supersymmetric indices, supersymmetrically protected three-point functions, and many other things. And so those can be computed either in supergravity or in string wood sheet theory on this side and compared to the symmetric obifold of T4. So that's the sort of old story. But in AdS3, it's a nice background because we can do more than in AdS5 or AdS4 or other AdS backgrounds, because we can focus on the background that has pure Nevers-Schwarz flux. So what that means is that we focus on a supergravity background that only has the metric turn on and a B field. And such backgrounds can be described by standard string perturbation theory. So in particular, you can write down the sigma model and you can try to solve it. So this was done in the case of AdS3, mostly in these papers by Maldacena and Guri, but there are also other earlier papers on this. And they allow you to compute, for example, the string spectrum exactly, at least exactly at small string coupling. And so on these AdS3 backgrounds, you can do many things that you couldn't do on higher AdS backgrounds. For example, you can just compute the spectrum and you can ask yourself if there's a CFT that does reproduce this spectrum. And so you can try to sort of explore the AdS-CFT correspondence from a completely different angle, because you can go and you can just produce a list of numbers that is the spectrum, and you can ask whether there's a CFT that reproduces it. And so in this spirit, I wrote this paper with Rajesh, who might be in the audience, and Matthias many years ago, 7 years ago now. And we realized that if you take AdS3 times S3 times T4, and with pure NS-NS flux, and you just put 1 unit of NS-NS flux, then actually if you compute the spectrum over here, it matches exactly with the spectrum over here. And later it was shown that also correlation functions match, and there have been many improvements in this matching and generalizations to other backgrounds, to other asymptotically AdS backgrounds. There has been lots of interesting development in the formalism. And generally this kind of special background where you only put 1 unit of an NS-NS flux is often called the tensionless limit in the literature now. So this is different from the tensionless limit that people consider in, say, the flat space, but it's the most tensionless point in moduli space in some sense. So in this, if you only put 1 unit of an NS-NS flux, in particular, the size of AdS3 is of order of string length. So that means that if you put some strings on AdS3, it can explore a lot of AdS, the AdS background, and you get winding strings, and you get all sorts of things that are very far away from supergravity. Okay. And so in particular, I want to mention one generalization that I think is important for this talk. Um, so if you play the same game, but now you put at least 2 units of an S&S flux on AdS3 times S3 times T4, then you can still compute the spectrum. And you can observe that the spectrum matches with a slightly more complicated theory. There's a symmetric orbifold of some particular linear dilaton theory times T4. And later in this paper, it was also realized that in order to reproduce the correlation functions, you actually have to turn on a certain deformation also on this boundary theory side. So I'll explain a little bit more what this theory means in the following slides, but I'll explain a simpler version of that. That's why I'm not writing a whole of all kind of details what this deformation exactly is. The only thing that I want to point out is that the center charge of this linear dilaton factor, this n=4 linear dilaton, is 6 times k minus 1. And the center charge of this T4 is 6. And so together this makes you up, this gives you a CFT whose center charge is 6k. In particular, if you put k to 1, then the natural limit of this thing is again just a symmetric orbifold of T4. Okay, but but this CFT
Lorenz.
will be more, yeah, please.
Hi, Raghu here. Question.
Yeah.
If you say plus deformation, right? Like then even in the previous case, you could have just said that it's sim n of T4 plus deformation because you have this 20-dimensional moduli space.
That's right. But what I mean is that here the deformation is turned on at the NS-NS point, whereas on the previous slide for sim T4, on the for the NS-NS point in moduli space, there's no deformation turned on.
Right. So what I'm saying is, in this case, do you know what the deformation is? It's some specific deformation?
Yes, I'm going to tell you in the next slide, I think.
Okay.
All right, but I'm going to tell you a slightly, well, it's actually the slide after, because first I'm going to simplify a little bit and talk about the more baby version. Because this background is rather complicated, and it turns out that most of the things in this background are actually not needed to understand what's going on. So instead, you can just focus on a bosonic string background. So you can take bosonic string on AdS3 times x, and x is anything that makes it so the only requirement on x is that it's a unitary CFT of center charge 26 minus the center charge of AdS3. So just meaning that this is a consistent string background. It has center charge 26, and I'll take x to be unitary CFT, maybe also compact. And so of course this is not a completely well-defined theory because the bosonic string has a tachyon in the spectrum, and that will eventually lead to inconsistencies in this kind of correlation functions and so on. But as long as we focus only at tree level, this works. And similarly, if you start if you start computing loop corrections, you will get divergent integrals, but you will get the same divergent integrals on the CFT side. So to understand what's going on, it's a useful thing to just think about this bosonic string. And I claim that there's a similar duality, except for the caveat of the tachyon, namely that there's a symmetric orbifold of a now ordinary linear dilaton theory, so it's no longer n=4, times the same theory X that appears on the bulk side. So this theory X appears in the worksheet description and also appears in the boundary description. And it really doesn't matter for this duality what X actually is. So linear dilaton theory, let's just recall what that meant. It meant that it's a free boson theory, but I'm adding an interaction. Well, I'm adding an additional term to the action that goes like q times r times x, where maybe I should write q times r times phi, where phi is this direction here, and r is the Ricci scalar. That changes the stress tensor and changes the center charge of the theory, but it's still a free theory. If you spell out what this requirement on the center charge is, it's 26 minus the center charge of AdS3, and the center charge of AdS3 is 3k over k minus 2. This is just a standard formula for the center charge of a WGW model, because the sigma model on AdS3 is a WGW model. And some very simple algebraic consequences of this is that first I have to tell you what this Q here is. So this Q is the slope of this dilaton, and it has some particular form that will become important in a moment. So it's k minus 3 divided by square root of k minus 2. And useful parameterization is in terms of this B, but it's not super important. And so in particular, if you plug this in, the center charge of this RQ times X turns out to be 6K. So you just plug in 1 plus 6Q squared. That's the formula for the center charge of a linear dilaton theory, plus the center charge of X, which is given by this formula. And you find that it's exactly 6K. And this is the value that you expect from, say, from like the stringy version of the Brown-Hinault center charge formula that was worked out by Givion, Kutasov, and Seiberg. Okay, so this is just a bunch of numerology at this point. But I claim that there's this duality, and again, I have to answer Raghu's question and tell you what this deformation is.
But
so
let me this duality for any k?
It's for any k, yes.
Not just for k equals 1 or k equals 2
right.
or whatever.
Yes. Yeah, in fact, for k2, so later, sort of what this talk will be about mostly is what happens when k is 1, or it's k to 3 in the bosonic case. But at k to 3, something special happens, and you can already see that because the slope of this dilaton goes to 0. But this works for any k. But sort of the point for the arbitrary k, it's kind of very complicated because you need to turn on this deformation, and like it's a non-trivial thing to consider bosonic string on this background. So all the correlation functions and so on will be very complicated. But
at k equal to 3, you will not have this deformation.
So you can choose. You can put it or you cannot put it, and so there will be 2 options. Yeah. So yeah, let me tell you what this deformation is. It's a marginal operator, and it comes from the twist 2 sector. So it's the symmetric orbifold has a bunch of twist fields, and in particular, the smallest twist field is the twist 2 sector. It just corresponds to the transposition in the symmetric orbifold. And it's a primary operator, so maybe I shouldn't have called this X, but it's this phi field. It's the linear dilaton field. So it's a primary vertex operator in the linear dilaton theory, but you take it in the twist 2 sector. So the symmetric orbifold works like this, that you have for every operator you could have written down in the original theory, there is a corresponding copy in any twisted sector. In particular, there's one in this twist 2 sector. And so this is the marginal operator. You can check that it has conformal weight exactly equal to 1. So that requires you to compute. There's a contribution to this conformal weight from the like bare twist field. And then there's a contribution because I turned on some momentum here. And you should notice that there's no I in the exponent here. It's just a real number. So this B was something like 1 over square root of k minus 2. So this is a real number. And so this means this marginal operator is a non-normalizable operator. It blows up as you take x to minus infinity. And you might also wonder, so in principle, there is a coupling to this marginal operator. But this coupling sort of doesn't matter what it is, because it's very similar to how you construct Liouville theory. Liouville theory you can construct from linear dilaton theory plus an interaction that looks very similar to this, except that it of course doesn't have this twist 2 sector here. And it has a coupling constant, but this coupling constant you can just absorb by shifting x. So you can set x to x plus a constant. There used to be a symmetry of the theory, and you can absorb whatever coupling constant is here. So it's true that so there's this coupling constant, but it doesn't actually appear in the theory. And you can also see that such a marginal operator has to be included in the theory. It depends what you mean by consistent CFT. But if you just have a linear dilaton theory, its spectrum actually doesn't close, its physical spectrum doesn't close under OPEs. Whereas if you add such a marginal operator, then it does become a consistent theory in the usual sense. Okay, so this is the operator you turn on, and you can test this duality. So how do you test it? You compute some 3-point function, 4-point function in the conformal feed theory, And you compute the perturbation theory in this operator. You compute the, say, three-point function. So this has been carried out up to fourth order in perturbation theory. And you check at every order that it matches the string theory answer. So the string theory answer is sort of exact. It is to all orders. And you can expand it in a certain sense. And you can check that if you expand it, it matches every order in perturbation theory. Very similar to how
Perturbation
you
theory in GS, or which perturbation theory?
It's a perturbation. It's very similar to the Coulomb gas formalism. So actually, what you're so if you compute say three-point function in Liouville theory, you can also compute that from the Coulomb gas formalism. And what you're actually computing is certain residues of certain poles. So there are these resonant poles. And what if you're checking this duality, what you're doing is you're extracting the poles of these residues, and you can check that they match exactly with these things you get in conformal perturbation theory. But there's no actual parameter you're expanding because this parameter sort of drops out.
Oh, that's what you mean, that you can test these things with some insertions of phi.
Yes.
Some number of insertions.
Yeah, you cannot sort of, I don't know how to construct this CFT sort of non-perturbatively. I can check order by order in perturbation that it exists and that it matches the string theory. I don't know how, like, also constructing Liouville theory non-perturbatively is quite difficult. Basically, you have to write down the three-point function and prove that it leads to something
You don't have
cross.
like the analog of the DOZZ formula. You just have the poles of the DOZZ formula.
I do have the analog of the DOZZ formula, but only at large n. So at leading order in 1 over n. But then, contrary to Liouville theory, there will be like a subleading 1 over n correction to the formula.
Okay.
So it's kind of more complicated. Yeah. Yeah. Actually, the three-point function looks very similar to DOZZ, except that there's some additional kind of combinatorics coming from this covering map story that you have in symmetric overflow. Good. So this is sort of the claim of this duality. But now to understand what the claim of the new paper is, you can observe the following thing. That when you put k to 3, and k to 3 is really what in the supersymmetric theory you call k to 1. So there's always this shift in k by 2 in the bosonic theory versus the supersymmetric theory. But at this point, this slope of the linear dilaton vanishes. And so instead of having a linear dilaton theory in the symmetric orbifold, you just have a free boson. And again, you should have in your mind that if you put k to 3, then the size of AdS3 becomes a fold of string length. And so now you can write down two consistent theories in the symmetric on the CFT side. So you have the theory that we just discussed. That's the symmetric orbifold of now just R times X plus a deformation. Or you can just take the symmetric orbifold of R times X, which of course is a consistent theory. So all the spectrum closes, and this one arguably is much simpler than this one. And this is claimed to be dual to this AdS3 times X. And so now you can ask, okay, so there should be like a simpler version of AdS3 times X to which this other theory is dual to, if you believe holography. And so this actually happens. And so the punchline of the talk is that there.
Another question on your previous slide. So the paper that you and Matthias and Rajesh had, that one is the dual side is just sim n, or is it sim n plus deformation?
No, it's only sim n, and like morally, it's of the same kind as the question mark I'm going to tell you about. Just when you
have the no question mark, right? You have both sides there.
Yes. So if you take this AdS3 times S3 times T4 for k to 1, it turns out you can only do the second option. This first option is not consistent. It will not lead to something unitary.
Okay.
But in general, there are backgrounds where you might have both options. So for example, for this bosonic, so for this AdS3 times S3 times T4, there was some other argument coming from supersymmetry that forced you to essentially take the second option. And also earlier than our paper, it usually was claimed that this background will be inconsistent because this first option essentially doesn't work.
Okay.
Yeah, so sometimes you're forced to take one or the other option, but yeah, sometimes you have both. So in some sense, there are two things you can call AdS3 at k to 3, I think, or k to 1 in the supersymmetric case. So to say this on a CFT on a CFT level is usually you say AdS3 for k to 3 will be described by the SL2R WZW model at k to 3. And strictly speaking, if we want to be precise, I'm talking about the WZW model based on the universal cover of SL2R. So really, maybe I should put some kind of tilde out. But I'll suppress this in the forum. This is so this is not what I mean by, so there are different theories with SL2R level 3 symmetry based on the different covers, but that's not what I mean in the following. So what I want to claim is that there are at least two crossing symmetric CFTs with this SL2R level 3 symmetry, one being the usual WZW model and one being the sort of special or WZW model. In particular, this has all the properties that appeared early in the literature. For example, it has this, its correlation functions will localize in moduli space, and the 3-point functions of this will be actually way simpler than the 3-point functions of this. So this is just a theory you get by specializing the standard SU2R structure constants to k to 3, and they sort of remain complicated. And correspondingly, there's also, I think there are two things you can consistently call AdS3. So they have the correct symmetries, and so these are some sigma models with these symmetries at k to 3. And remember this, like geometry doesn't mean that much in this limit. So I think, yeah, both of them are fine string backgrounds. So I don't think there's any reason to discriminate one versus the other.
To the example with the AdS3 times S3 times T4. So there the sigma model does localize, right? Like there are these delta functions.
Yes.
So that's like the primed version morally, or?
That's right, yes.
And you said there's no other version in that case. That's just the only one.
Yeah, because in that case, so we couldn't actually describe it in the RNS formalism. So we had to go to this other formalism, this hybrid formalism. And there you could see basically, because in the RNS formalism, there's a problem with unitarity, usually if you put k to 1, because there's some SU2. So the problem comes from the SU2 factor, actually, that there's some tension with unitarity. And the only way we know how to repair this unitarity is if we sort of restrict the spectrum. And once we restrict the spectrum, we are morally talking about this theory. But we're really talking about some supergroup theory. So it's a little bit more complicated to describe it there. But I think morally it corresponds to this prime one.
Just one more thing. Do you think there's also this SL2R and SL2R prime for larger k, or just for k equal to 3?
It depends a little bit what you mean that there is. So there is, this also exists for larger k, but it's a theory very much analogous to the linear dilaton theory. So it has a spectrum. So if you take the 3-point functions, it doesn't actually close on the physical spectrum. So if you take the OP of two operators, then you would get kicked out of the spectrum. And only for k to 3, you stay in the spectrum. So if that doesn't bother you, then the answer is yes. If it bothers you, then the answer is no.
Okay, thanks.
And in fact, yeah, so let me just mention this. So there was sort of the reason why we wrote this paper, maybe, was that Matthias wrote an earlier paper with his student, Witt. And they came up with this duality, that AdS3 times S3 times S3 times S1, which is another maximally supersymmetric AdS3 background with k to 1. So the level of this AdS3 is 1, or in the bosonic language, it's 3. And then the flux through both these three spheres is 2. And you can show that this leads to a consistent string background. And they observed that the spectrum matches exactly with the symmetric orbifold of free non-compact boson, a free compact boson, and 8 free fermions. But this is like a free theory. So the only way that this is going to match, the correlation functions are going to match with this background, is if you take the primed version here. And there's also much more complicated version of this duality. If you don't take the prime here, then you have to add a deformation on this side, and it gets much more complicated. But this is a case for the superstring where you have both options. And so once I wrote this paper, there was another paper that strongly disagreed with this duality. But I think it sort of is explained by putting this prime here, and then you have a consistent string background to correct correlators and spectrum. You should also already notice that. So here we wrote R. So this R turns out to be actually, if you write AdS3, this cannot never be an R because there's reflection symmetry. Reflection symmetry identifies incoming and outgoing waves in this rate. This is like the radial direction in AdS3, and so this cannot be literally correct without doing something funny in AdS3. Anyway, another point where this appeared early in the literature is there was this formalism that was developed by Knighton and Sri Pragya, and they computed correlators in AdS3 by some free field methods, and they noticed that there's always a leading term to this correlator, which they called the near boundary approximation, and this near boundary approximation becomes exact when k is 1. And it basically it's basically the correlators of this AdS3 prime theory. Okay, so for the rest of the talk, so this was sort of a very long introduction / background. I want to explain a little bit more about the SL2R WCW model and what this SL2R prime WCW model means. In particular, I want to convince you that it's a crossing symmetric theory and it exhibits this phenomenon of correlators localizing in modular space. Okay, any other questions at this point? Okay, good. So then let's get started. And so it's always a little bit difficult to introduce this model. It's just because there are many sort of parameters flying around. So what I decided to do is to tell you what the vertex operators are, and then what the structure of the correlation functions is. And there's sort of lots of fine print in there that please feel free to ask me about. But I decided to focus on the vertex operators directly. So a vertex operator in this theory has many quantum numbers. Let's start with quantum numbers that we're familiar with. So of course it depends on the worldsheet location where we insert it on the worldsheet. And it also carries an SL2R spin. So this is very much analogous if you ever thought about the, say, SU2 WCW model, then vertex operators will be labeled by an SU2 spin. And this SL2R spin, which I'm calling J, has two options basically, because in SL2R we have two different kinds of unitary representations. We have the so-called discrete series representation, where this J is real and in some particular range. And that describes, from the point of view of spacetime, it describes short strings. So for example, the graviton, the dilaton, and so on, those would all come from this range of J's. And then there's also the second option where you take J to be in this 1/2 plus imaginary line. These are the principal series representations. And they correspond to long strings in AdS3. Because in AdS3, you can have there's basically a B field that tries to push the string outwards, and there's the tension of the string that tries to contract the string. And you can have it in AdS3 that you have a string that goes outwards forever, because the B field can beat the attraction coming from the tension, the contracting force. And so that this spin J here can be any continuous value corresponding to roughly the radial momentum of the string. And on top of this, you also have this an integer quantum number, the spectral flow number. So this takes integer values, and it describes the asymptotic winding of the string. Because in AdS3, the asymptotic spatial region is just a disk, and the string can wind some number of times around this asymptotic spatial region, which is captured by the spectral flow. There's also a representation theoretic way of introducing that, but it's always slightly confusing. And essentially, these vertex operators, they're not usual highest weight representations when you turn on the spectral flow prompt. And finally, there are other labels in this vertex operator, but they're not labels of the representation, but they're just labels like the magnetic quantum number, so where you are in the representation. So one of them is the space-time conformal weight. They're basically the analog of the magnetic quantum numbers. The left-moving space-time conformal weight and the right-moving space-time conformal weight. So they come because there's the zero-mode algebra of the SL2R. There's the SL2R zero-mode algebra, which is identified with the conformal symmetry in target space. And those operators, they transform under some particular spin. And finally, also it's useful to introduce this space-time coordinate so that the vertex operators not only depend on the worldsheet coordinate, but also on the space-time coordinate, which I call x. And it just takes values in the Riemann sphere. So in particular, if you perform Mobius transformations in this x, then you will get the usual Jacobians raised to the conformal weights out front. So those vertex operators transform under two different Mobius symmetries, under the Mobius symmetry in x and Mobius symmetry in z. And in z, those will also have some definite conformal weight. So this is the worldsheet conformal weight, which is different from the spacetime conformal weight. And it's not independent. You can compute it through all the other quantum numbers. It takes this form. So that follows just from the representation theory of the affine SL2R. Okay, so I know this is kind of looks a little bit scary, but so the things that we want to compute are the correlation functions of these things. And before I tell you how that works, I'll first tell you why that makes sense from the point of view of holography and why all these parameters are sort of natural. Because what we want to compute in string theory is our correlation functions of these operators. And we also take AdS3 times some x. So there's some internal CFT x, which will also have some vertex operators, which I'm just calling OI. So these are just supposed to be some primary operators. And then the combined vertex operator is the one that we just wrote down on the previous slide, tensor with some OI from the internal space. And then we take n of those, and we take the correlator on some Riemann surface. We want to integrate over the moduli space, and we're summing over all the genus. Sorry. Okay, and so this, so holography tells you that this should be equal to another CFT correlation function, namely the CFT correlation function of the boundary. And how this works is, first of all, not every vertex operator classifies, because to be a good string theory vertex operator, you needed that the worldsheet conformal dimension has to be equal to 1. And once you impose that, then it's basically an equation for this h and h bar. Because if you go back to the previous slide, you're imposing that this combination is equal to 1. So, and typically we think of solving this combination in terms of h. Okay, so this basically eliminates these parameters at h. And you also eliminate the parameter z, because z is one of the moduli that you integrate over. So those z's you all integrate over. And so what you end up with in the end is just an object that depends on the x's, and it depends on the j's and the w's. And this precisely matches to the correlation, at least on the level of the quantum numbers, it precisely matches to the correlation function in the symmetric orbifold of this linear dilaton theory times x. So you just still get the same vertex operator in x. And here you get a primary vertex operator in this linear dilaton theory. So it's just some operator with some fixed momentum. And the momentum is determined through this j. So it has some particular formula, but it's just basically the same as j. And finally, the w here translates into the twist on this side in the symmetric orbifold. Okay, so this is how this works. And on this side, there's this parameter gs, which translates to the n roughly on this side.
So this wi comes on OI as well on the CFT, even though in the string theory side, the w is only a property of the v.
Yes, it comes also here, essentially. So you take this operator, which is in the untwisted sector, and then you use the copy. You take the copy that is in the twisted sector. But it's, yeah, so this wi also matters for this OI piece.
A little bit interesting how that would happen, right? Because on the worldsheet side, it's only the SL2R part that knows about the W.
Right. The main reason why this happens is that the surfaces on which this is evaluated are different. So on this side, you'd have OI of ZI, and here you have OI of XI. And that happens. So in this localizing theory, it becomes easy to understand why this happens. In this non-localizing theory, it's much more complicated, and you just observe that it works. But yeah, essentially what happens is that these ZIs in the localizing theory get coupled to this XI, but there's like a bunch of like conformal factors and so on that appear. And the way you compute something in the symmetric orbifold is usually you lift it to all possible covering surfaces. And then again, you're basically computing OI of ZI, because you should think of the covering surface as being the worldsheet, but you pay with some conformal factors that appear in front. Yeah, so that's why sort of this W knows. It doesn't know about the specifics of the OI, it just knows about the conformal weight of OI, essentially.
Okay.
Yeah, I just wanted to ask on the right-hand side, how does one see the genus expansion? Is there any way?
Yes, the genus expansion becomes a 1/n expansion on the right-hand side. So in this, when you compute in this symmetric orbifold, some correlator, then again you have to lift it up to this covering surface, and the covering surface might have it might have genus 0, but might also have higher genus. And when it has higher genus, then it corresponds to terms in this genus expansion that are subleading. There are some caveats I'm sweeping under the rug that you can try to point it out. But yeah, essentially this duality, it doesn't work exactly at fixed n. There's something you have to do that actually what this computes is in this grand is computing not at fixed n, but it's rather computing in the what's called the grand canonical ensemble, which means that computing in this string coupling doesn't correspond to 1/n, but it corresponds to the chemical potential associated to n. So this map is slightly more complicated than I'm making it out to be. But for tree-level quantities, for example, this doesn't matter that much.
And this correspondence works for the bosonic example as well?
Yes, so this is written down for the bosonic, and again, there's the caveat that at genus 1, this integral is not literally convergent because there's a tachyon. And similarly, also here it's not convergent anymore because you're adding marginal operators, and when you add the marginal operator, you have to integrate over the location of the marginal operator, and that integral is also not convergent. But you're sort of matching the same divergences on both sides. And if you want a completely well-defined theory, then you need to talk about super strings, then it just works. But it adds various complications like picture numbers and things like that. It's just technically more complicated. But there's actually a paper that has checked it now, also for the superstring, by Cheng Peng and his student.
Oh, thanks a lot. And the divergences can actually be compared and matched?
It hasn't been done, but I would expect so.
Thanks. Thanks a lot.
Yeah. Okay. Great. Okay, so hopefully it makes sense to look at these operators. And so basically the basic object in the worldsheet that you want to know is the 3-point function of these operators. And that can be found by doing some analytic bootstrap analysis. And it's again very much analogous to.
Just to sort of, so far you've been discussing the AdS3 model, not this AdS3 prime model.
So far it didn't matter what it was.
Okay.
So far I just discussed theories with SL2R symmetry, if you want.
Okay.
Yeah, but you will see in a moment where the difference appears. So what has been done in the literature is to bootstrap this 3-point function. And basically it was done for W to 0 in this paper by Teschner. And there it's very similar to the DOCZ formula of Liouville theory. This was then generalized to Malus and Aguri by Malthus and Naguri for some 3-point functions of low W, and then we gave the general formula. But the general formula is kind of complicated. But the answer is complicated, so I'm not writing it. But what I want to point out is that there are some assumptions that go into this bootstrap analysis. One is that the spectrum is diagonal, which means that every operator appears only, so it has in particular the same left moving spin and right moving spin and same left spectral flow and right spectral flow. So you only have, and every operator only appears once. Then one also assumes that for this bootstrap, it's important that there are some degenerate operators and they have some null vectors, and you get some additional constraints from those. So in the case of Virasoro, this is known as the BPZ equation, and you can use the BPZ equation to bootstrap the theory. But in particular, to do that, you need to assume that the answer is analytic in both Ji and all the spins and in K. So there's some assumptions on the behavior of the 3-point function that goes into this bootstrap. And once you assume that, you get a unique solution out. And the solution is complicated, so I'm not writing it. But the point is that this AdS3 prime, first of all, it only exists for K to 3. So already this continuity assumption in K goes out of the window. And similarly, it will turn out that the answer is also not continuous in J because it features some delta functions. So basically, there's a sort of an AdS3 sigma model that works at generic parameters, and then there can be more that work at special parameters. And so one way to get this AdS3 prime model is to look at the analytic structure of the 3-point function. And this 3-point function turns out to have a bunch of poles in the sum of the spins. When the sum of the spins takes some particular value, then there's a simple pole in this 3-point function. Similarly also for higher point functions, but let's just focus on the 3-point function. And in this correspondence, in this holographic correspondence, those correspond to poles in this momentum along the linear dilaton direction in the symmetric obifold. And those poles you should have expected, because if you turn off the deformation, then there should be, of course, momentum conservation in this factor. And so that actually tells you that in the undeformed theory, you would actually get a delta function in the sum of the alpha i's. And once you turn on the deformation, this delta function gets spread out, gets smeared out into a pole. And in fact, there's not only one pole, but you get one pole for every order in perturbation theory, roughly speaking. So this, again, is completely analogous to what happens in Liouville theory if you construct Liouville theory from the linear dilaton. And now there's this very simple ways to sort of turn off the deformation in the symmetric obifold. And how you do that is just by extract the residue of the leading pole. So there's a bunch of poles, and the leading pole is the one that comes from the undeformed theory, where it's just a momentum conservation in this part. So it occurs when the sum of these alphas is equal to Q, the background charge. And on the worksheet, that means something that the sum of this J's is equal to K over 2. So the idea is now you just take on both sides of the duality. So you have complicated functions on both sides, but you just take a residue on both sides, and you should still get a duality. So if you do this on the worksheet, you get these primed correlation functions, and they have this delta function where the sum of the spins is equal to K over 2. And then you need to, from the generic 3-point function, you just need to extract the residue. And you should observe that this is only possible for special spins, because the sum over spins minus K over 2 being 0 only works when the spin is 1/2 plus something imaginary and K is 3. Just because the real part, if you look at the real part of this equation, it tells you, if they're all in the principal series, it tells you it's 1/2 plus 1/2 plus 1/2. And so K has to be equal to 3 for the real part of this equation to work out. And then the imaginary part of this equation is just momentum conservation in these P's. And so what you will need to do is to restrict the spectrum to the principal series, which corresponds also to the usual vertex operators in this free boson part in the dual CFT, and K to 3. But to say, like, to answer, come back to Raghu's question from before, if you don't care that this delta function cannot be true, I mean, in the physical spectrum for k not equal to 3, you can still write down these 3-point functions for general k, and it will still lead to something crossing symmetric. But you will need to analytically continue in the spins too. So this is a bit of a formal delta function. Good. So that's the procedure. And the slight miracle that happens is, even though this 3-point function is kind of ridiculously complicated, once you take this residue, it simplifies a lot. And so what it simplifies to, first of all, is convenient to label the vertex operator now by this p. So this was just a spin as 1/2 plus ip. And then this sum of the j's, this delta function of the j's, becomes momentum conservation in the p's. And then you get some simple factor here. So, okay, maybe it doesn't look dependence on p, which is already kind of amazing, because before there was some. And also, yeah, sometimes you also get 0. So some cases, this limit is 0, this residue is actually not there. So there's some triangle inequality in the w's that has to be satisfied, and also the sum of the w's has to be odd.
Sorry, clarificational question.
Yeah.
So, in the theory with the AdS3 times S3 times T4, you said that's like a prime theory, like one of these AdS3 prime, but there I thought you don't have this p parameter, right? You only keep the state with j equals 1/2.
That's right. Yes. Yes. So there it's more, even more special in some sense. There you put all the p's to 0 on top of this. Yeah.
Okay.
But also there, the dual CFT doesn't have this R factor still there.
Right.
It's just symmetric overflow of T4, not R times T4. Yeah. Good. Yeah. And these parameters on the right-hand side, there are some explicit things. It doesn't really matter that much, but the way that you're computing them is through this covering map. So what is the covering map? So you're computing a 3-point function where I put the 3 x's and 3 z's to 0, 1, and infinity here. And the covering map is a map from CP1 minus these 3 points to CP1 minus these 3 points. And it's ramified over these 3 points with ramification indices W1, W2, and W3. And in particular, these conditions here are the geometric condition for this covering map to exist. And when it exists, there's exactly one of those, and those are some Taylor coefficients and some coefficients that enter into this covering map. The details don't really matter. But it's something that is completely determined through geometric quantities. Okay. Good. So this is the sort of the 3-point function. Yeah.
Question. Since you've restricted to the principal series, what happens to the short strings here?
Right. So short strings turn out to never be produced in like 4-point functions. So ultimately, you can ask yourself, well, you could have written down this expression also for short strings, which would have corresponded to imaginary p's. But you see that if you have like 2 real p's, like 2 long strings, because of this delta function, you can never produce a short string. So the long strings are a consistent sector. You can ask if you can add short strings to that on top, and it seems like the answer is no. You wouldn't get a consistency. But yeah, it's something you need to look at model invariants and things like that to decide. Okay. Great. Any other questions? Okay, this last part is pretty short. So I just want to convince you now this is a consistent theory. So I did something slightly funny. What I'm checking, so model invariance is kind of subtle because it's a non-compact theory, and computing higher loop things on the worksheet is difficult. But what I will do is to check that the 4-point function is crossing symmetry. And so if you write down the 4-point function now of these funny vertex operators with the prime, then if you're an honest person, how you should obtain it is to do a conformal block expansion. Meaning that here I'm slightly schematic. So you take a 3-point function and you take another 3-point function and you take a conformal block squared and you sum over all possible internal states. And that sum would include a sum over the spectral flow parameter and an integral over the momentum. And this conformal block here keeps track of all the descendants. So we're going to do this in a moment, but I'm first telling you the answer of this computation. So if you do this computation, what you get is still a pretty simple formula, which I think is quite remarkably simple because usually 4-point function is much more complicated than 3-point function. Here it's kind of similar difficulty. And let's first look at this formula. Maybe I copied it again here, I think. It's the same formula. So the 4-point function, first it has still a momentum conserving piece, which makes sense because if you multiply 2 3-point functions, momentum is still conserved. Now you get also finite sum over covering maps. So before, for the 3-point function, there's at most one covering map, so there can never be this sum. Now there's a finite sum over possible covering maps. And those are still maps from CP1 minus 4 point removed to CP1 with 4 points removed, with ramification indices W1, W3, W1 to 3, 4. But the thing on top that you have is now you have the 4-point function depends on trivial and the cross ratio. And what appears is a delta function in Z in the cross ratio, which nails it to sort of the cross ratio at which this covering map exists. Because generically, if you take CP1 and you remove 4 points to another CP1 with 4 points removed, and you specify what those 4 points are, then typically there's no map between one and another. So that's a fact that you know very well. If the ramification indices are all 1, then if you take CP1 with 4 points removed to CP1 with 4 points removed, there's only map when the two cross ratios are the same. That's basically how the cross ratio is defined. And similarly, if you add more complicated ramification, like that the map near one of the points looks like z to z squared, it's still only true that there's a finite number of solutions what the cross ratio of CP1 can be expressed through the other cross ratio. So this is some algebraic problem. But the point is that there are these delta functions. Then you get a free boson correlator on top, and you get again very similar conformal factors as you had before. And this is essentially the same formula, not quite as Raghu correctly noted, as appeared in AdS3 times S3 times T4, where the level is 1. And there basically the only difference is that this delta function is not there. But morally it looks very similar, that you have this localization in modular space for the wedge sheet theory, and you get some conformal factors. And when you have this localization, you can see that the integral becomes very simple, right? You have to compute the integral over the modular space of surfaces, and this integral just collapses to a finite sum because the integral gets played against the delta function, and it just becomes this finite sum, and this finite sum is what you get in the symmetric orbifold. All right. So, but you can see it also already happened for bosonic model. So this localization has in some sense nothing to do with supersymmetry. So this is what I just essentially said. But so the form of this 4-point function makes this match with the symmetric orbifold of R times X essentially obvious. So if you take the 4-point function, this was the formula on the previous slide, and you multiply it by a 4-point function of the internal CFT, because the full vertex operators in the wedge sheet are again products to vertex operators on SA2R and the internal CFT, and then you integrate, then you get something simple, and what you get is just these conformal factors here, and then you get the vertex. This is a free boson correlator, so you can write it as a correlator of free bosons, which I just called VP. Tensor this OI, but these don't live at any Zi anymore, but they live at the special Zi that you have on the covering space. So maybe this also answers Raghu's question from before, how this Wi sort of matters for this OI. And this is the sort of standard formula in the symmetric orbifold for correlators. You need to sum over all possible covering maps. You get certain conformal factors. Those were computed by Looney and Matur in 2000. And then you get the correlator on the covering surface. Okay, so the last thing I think I have to explain to you is why the sum over conformal blocks leads to this special 4-point function. And in particular, the 4-point function, I should say that we wrote down, it's manifestly crossing symmetric. So it doesn't depend whether you start in the S or T channel. So what remains to compute is the sum over W's and P's with two 3-point functions and conformal blocks. And let's recall how conformal blocks are actually defined. So what this formula is just doing is inserting a complete set of states in the middle. So it's just a complete set of states. Let's call it psi here. That can be now primary states or descendant states. It can be just any state in the CFT. And it lives in the representation labeled by W and by P. And you just sum over all, like an orthonormal basis of such states. And if you do the sum, you get the full 4-point function. If you look at the sum, so usually if you do this in a theory with Virasoro symmetry, the sum converges when Z, the cross ratio, is less than 1. Here you have both X and Z, so you have to be slightly more careful. Turns out to converge when Z is small. I don't know whether less than 1, but it's small. And at fixed, you keep this product of X times Z to the W fixed. So you take both X and Z small, essentially, with this fixed. And so to compute this, there's sort of two ways to do it. There's sort of the dumb way and there's the smart way in some sense. The dumb way is just you brute force compute these 3-point functions and you try to sum it up to whatever level you can, and you see whether it agrees to that level with the previous formula.
I didn't quite understand what you meant by expansion in Z at fixed XZ to the W.
I just mean like if you do this expansion, it's like an expansion in the cross ratio, right? Just like in usual conformal field theories. And so you get, so for this to converge, usually it depends whether you talk about the elliptic frame or not and so on, but let's just do the dumbest possible thing. We just take the 4-point function and you expand it for small cross ratio. So this is an expansion in Z to the N. Right. So you want to take Z small enough so that this converges. In this case, you have both the Z and X in the game. So what you want to do is you want to take Z small, but you want to keep this combination fixed, turns out.
X is becoming large somehow. If Z is this is fixed, then X is large. Are you taking?
Yeah, you can take X large. You can also do it the other way around. You can also add -1. There's one way to map one to the other if that bothers you. Then you can take X and Z small.
Point of view, X is just a label, right? So
Yeah.
normally I would have expected that just fixing X, it should be convergent at small z.
Right. The trouble is that these representations that appear in the middle are these spectrally flowed representations. So their energy is not bounded from below. Their energy is only bounded from below at fixed quantum, fixed, let's say fixed energy, fixed like eigenvalue of the Cartan of SA2R. And that
do a double expansion in Z and X.
Yeah. Okay. Yes, but it's not really double expansion because these are principal series representations, which basically means that in one direction the sum goes to -infinity and +infinity. And so you need that sum to be of order 1, the parameter. And then there's one expansion in which the parameter is small.
Okay.
Not sure what
Okay, let me just summarize. What you're trying to say is that this is Z to the W over X. So if Z is small and I want to keep that fixed, then X should also be small, right?
Yes, yes. But it's a bit funny because this W actually depends on which term you are in the sum. So that makes it a bit funny.
W is always positive here or what?
Yeah.
Okay.
Okay. But so basically how this works is that, so what you need to compute are these three-point function with a general descendant. And there's some recursive way of doing that, which I won't explain because it's a bit technical. But basically, you can put any descendant here, and you can recursively remove it. This is the same as for, say, three-point functions of Virasoro symmetry, but you have to work much harder because there's a spectral flow in the game. So the spectral flow just makes it such that these three operators are not normal highest weight operators. And so it's not as trivial as removing negative modes. But you can do it. And then you can check that to this order. So we checked it sort of in the dumb way to next to leading order. So there's a leading order where you just keep the primary here. And then there's the next to leading order where you keep level 1 descendant. And to this order, it works that the sum becomes this delta function expression. And let me just tell you how this works. So the delta function here is kind of obvious because there's a delta function of P1 plus P2 plus P. There's a delta function of P3 plus P4 plus P. And you integrate over P. And so that puts P to be, say, minus P1 minus P2. And the delta function becomes a delta function in the 4Ps. There's also this the sum over gamma. The sum over gamma is just the sum over W that appears here. It's just the sum over possible intermediate spectral flows. But maybe most non-trivial is where this delta function comes from. And it comes because in the sum, in this expression, you also have to sum over these H quantum numbers of the vertex operators that are suppressed in the notation. So these vertex operators also depend on H and H bar, both of those. And you have to sum over this H and H bar, and that's not bounded from below or above. So that's this kind of sum that looks like this. Like a sum over some parameter that is of order x to the minus 1 z to the w. So this is where this comes from, to the h. And you're summing this over h. So formally, this gives a delta function in something like x minus z to the w with some additional terms. So this is where formally these delta functions come from, that you have a sum over h, and the sum over h is not bounded from above or below. And if you do it with h and h bar, it turns into delta 2, and this h minus h bar is not completely independent. So this is where this delta function ultimately comes from. And then you have this, this free boson factor comes from doing the proper computation essentially, and similarly does. So for this to work at subleading order, you have to know various identities that relate these quantities for the full punctured covering map to 3 punctured covering maps. But okay, you can kind of do it. So this is kind of cumbersome to do. It took us a long time to actually only do the next to leading order. You can also do something much smarter in some sense. You can determine the result of this computation because you know all the crossing properties of this kernel. And because you know the crossing properties, you can see that this combination actually has trivial crossing properties, and then you can just match it to, you can fully fix the result from this knowledge. So, but let me not explain that. Hopefully you believe me that this is a correct identity, and once you know this is a correct identity, then this expression is crossing symmetric, and then you sort of win. Okay. So I'm sort of out of time. So let me just make one last comment that I think is kind of interesting. Namely that this is a bosonic string theory that I talked about. So this AdS3 prime times x. And it has a fully consistent dual CFT, namely the symmetric orbifold of R times x. So there's nothing wrong with this, even at higher genus. And that should be very surprising to you. At least it was surprising to me, because that's contrary to the lore that whenever you have a bosonic string with many degrees of freedom, that there should be a tachyon in the spectrum that should kill the string. And usually this tachyon would show up as a divergence once you try to do this moduli space integral, because the integrand blows up near the boundary of the moduli space. But here this doesn't happen because the integral localizes, and it never localizes to the boundary. It always localizes to places in the middle of the moduli space. And so this is actually fully consistent bosonic string without any tachyon in the spectrum that would screw it up at higher genus. Yeah, so I don't know any other example of this. So I find it kind of interesting. Okay, so that's it. Let me just give the main punchline again that maybe you can remember, is that it turns out that there are two consistent models that you can call SL2R level 3 and SL2R prime level 3. And one describes what you would usually think of as AdS3 times X, and it's dual to the symmetric orbifold of RQ times X, with this particular deformation that comes from the twist 2 sector. Even though I don't know how to like fully non-perturbatively define the CFT, but you can check order by order that it works. And when you're sitting at k to 3, there's a simpler option, namely AdS3 prime times X. And it's just dual to the symmetric orbifold of R times X without any deformation. Yeah, thank you very much.
I have one question about this modular invariance. In principle, one should be able to check something like it, right? Because even in Liouville, even though it's non-compact, there's some infinite factor, but then times a modular invariant function.
Yeah.
So is there any hope here of doing this for this AdS3 prime theory?
Yes, there is, I think. So let me first say what's known about AdS3, just usual SL2R. So if you compute the one loop partition function, you encounter a similar problem. And in some sense it's worse, but so usually what people do is, because you have also an SL2R in the game, you can turn on a gauge field, SL2R gauge field around your torus, so that your torus partition function is not only a function of tau, but it's also a function of this background gauge field. And then so a similar thing happens as in Liouville theory. There's some infinite prefactor, and then you get some term that looks almost like a free theory. So instead of 1 over eta 1, 1 over eta that you get in Liouville, you get 1 over theta 1, like the first theta function. And that's formally is modular invariant. But then there's a story that is in the second paper by Maldacena, Son, and Huri, where it's not completely obvious from this formal expression how you would extract back the physical spectrum of short strings and long strings and so on. So that expression, in fact, is derived by doing some path integral computation. And so basically, a punchline is that this expression has various poles. So it looks like 1 over theta 1 of z comma tau. So it has a bunch of poles when tau goes to some special values, just because theta 1 has various seeds. And basically, the pole on the long strings come from the poles of the expression, and the short strings come from the rest. And what you can do formally is to replace, instead of having 1 over theta 1, you can replace that with the delta function supported at these special locations, and it's still modular invariant. So this is what happens formally if you consider only long strings. And you can write that down, and it's still modular invariant and so on. In fact, long strings and short strings, they never mix in the modular invariance in this formal sense. You can have a sort of model with only short strings or only long strings. Yeah, so you can kind of do that, but yeah, I'm not sure how much it convinces me that this is a good test to do.
What about this W? I thought normally this W has both signs, but
yeah, right. So that's another issue I swept under the rug, is that so what we're doing here, we have to be a bit careful, because I talked about SL2R WCW model, but then I made this X that appears, I made it complex. So really, and it matched it to Euclidean target space correlators. So that in principle is not a legal thing to do, because this is the worldsheet theory that describes Lorenz in target space. And why this is important is so that basically what happens in the Lorentzian theory, you're talking about you have both negative W and positive W. And the negative W you should think of as ingoing strings, and the positive W as outgoing strings. So Lorenz and AdS is some long cylinder, and you have the strings that come in and the strings that go out. Whereas in Euclidean, in the Euclidean theory, you're really talking about something SL2C. It's not SL2C WGW model, but it's the analytic continuation of this theory to Euclidean target space. Once you're in the Euclidean target space, there's an inversion symmetry in the dual CFT. You can send like x to 1 over x, and it exchanges incoming and outgoing strings. And in fact, negative W and positive W turn out to come from the same vertex operators. So you can just do the inversion in x on these vertex operators and it turns around W. So in that sense, there's no need to talk about negative W in the Euclidean theory. And it also caused a whole lot of confusion in literature that there's this sort of, the Euclidean theory is not, so on the level of the spectrum, it appears from analytic continuation of the Lorentzian theory, but it's not that, but the relation between the two theories is quite complicated. So in particular, there are 3-point functions you can compute in the Euclidean theory that don't seem to have any analog in the Lorentzian theory. And the fusion rules are completely different and so on. So it's a bit complicated.
You also don't have W equal to 0, or you have that?
You do have W to 0, but they don't lead to physical string states because W to 0, their conformal weight is always positive, and you cannot satisfy the Maastricht condition.
Okay, thanks.
Yeah, I got a little confused about the tachyon divergence. So because of the localization in the moduli space integral, so the tachyon divergence eventually does not appear, does it? I mean, or not?
That's right, yes. It doesn't appear.
So therefore, so the issue of comparing the tachyon divergence on both sides, that...
Right. So it's an issue here in this first theory. So you have a tachyon on both sides, and both sides diverge. But on this theory, it doesn't appear. So because here, this is localizing in modular space, so the tachyon is not a problem. And similarly, this, of course, is a well-defined theory. It's just a symmetrical default of a well-defined theory. But here, this deformation leads to divergences. And you can check that there is a divergence. I haven't tried, or nobody has tried, I think, to like match divergent pieces to divergent pieces.
Okay, thanks a lot.
Yeah. But to me, this is just a sort of toy model for the superstring where you don't have to deal with some of the problems that you have there.
So are you saying that the tachyon is just not there in the spectrum in the second case, or that it does not appear on internal?
The tachyon is not there, yeah.
Just not there in the spectrum.
So the tachyon would come from the so that's actually the only state. So when I just answered your previous question, I slightly lied because in the bosonic string, the Maastricht condition is the Wurtz conformal dimension is equal to 1, which you can satisfy in the W to 0 sector, but you can only because here you go. Let me just correctly answer you once. So yeah, so this is the formula for the Wurtz conformal dimension. If you put in W to 0, all these things disappear. And you see that if you also put J to 1/2 plus something imaginary, this is strictly positive. But you can still make it equal to 1. So there's a solution where you solve for J such that this becomes equal to 1. But you cannot put any descendants on top because you cannot make it, if you add +1 from a descendant, you cannot make it equal to 1 anymore. So there's exactly one state from the untwisted sector, unflowed sector, that you have in the usual AdS3 string theory. And that you should think of as being the tachyon. So that's the state that leads to divergences. Whereas in this prime theory, it's never produced in the OPE. So you can just consistently forget about it.
Okay, if there are no more questions, let's thank Lorenz again.
Right. Thanks a lot.
Thank you, Lorenz, for a very nice talk.
Yeah. Thanks. This was clear and good.
Good. I'm also happy to stick around if there are any other questions or something.
Yeah, I think we can maybe turn off the recording and have a
Yeah.
normal